The Big Bang is usually described as the moment everything began: space, time, matter, energy. But that idea is misleading, because the Big Bang was not an explosion in space. It was a transformation of space itself. And once you understand what actually happened, a deeper question appears. Did the universe really have a beginning, or did time itself come into existence later? To answer that, we have to follow the evidence, not myths, all the way back to the limits of physics. Look up at the night sky, not as a scientist, not as a philosopher, just as a human being. Every point of light you see feels distant, silent, eternal, as if the universe has always looked this way, but it hasn't. Everything you are seeing is the aftermath of a transformation so extreme that our everyday intuition simply breaks. Not an explosion in space, but a transformation of space itself. We are taught to imagine the Big Bang as a massive blast, matter flying outward into an empty void. That image is comforting. It feels familiar. It feels like something we understand. It is also wrong. A better way to think about the universe is not as debris rushing through space, but as space itself stretching. Imagine an infinite loaf of raisin bread baking in an oven. Each raisin is a galaxy. As the dough expands, every raisin moves away from every other, not because they are flying, but because the dough between them is growing. There is no center, no edge, no privileged location. This is what cosmic expansion actually means. When astronomers first discovered this, they didn't see galaxies moving directly. They saw something subtler, a stretching of light itself. Light arriving from distant galaxies was shifted toward redder wavelengths, like the lowered pitch of a train whistle as it moves away. The farther a galaxy was, the more its light was stretched. Distance and recession were linked. Run that relationship backward, and the picture becomes unavoidable. The universe was once smaller, hotter, denser, more extreme. Push it far enough, and you reach a state where matter, energy, space, and time were compressed into conditions unlike anything we experience today. This is what we call the hot Big Bang. Notice the wording, not the beginning of everything, a phase, because here, physics begins to hesitate. The equations that describe expanding space, born from Einstein's theory of general relativity, work astonishingly well. They describe how matter and energy curve spacetime and how that curved geometry evolves. Gravity is not a force pulling objects through emptiness. It is space itself telling matter how to move. And when those equations are pushed to their limits, they reveal something unsettling. They point toward a moment where density becomes infinite, temperature diverges, and the very concept of time dissolves. A mathematical singularity, a signal that our description of reality has broken down. Not necessarily that reality itself has. What we call the Big Bang may not be a true beginning at all. It may be the edge of our understanding, a boundary beyond which new rules apply. And to glimpse what might lie beyond, we must look not forward into space, but backward into the deepest structure of reality itself. To understand why the universe expands at all, we have to let go of a deeply ingrained idea. That space is just an empty stage where events happen. According to Einstein, space is not passive. It is dynamic, flexible, responsive. Mass and energy do not move through space, they reshape it. This is the core of general relativity. Instead of gravity being a mysterious force pulling objects together across emptiness, it is geometry doing the work. Matter and energy tell space-time how to curve, and that curved space-time tells matter how to move. The analogy often used is a stretched rubber sheet. Place a heavy object on it, and the sheet dips. A smaller object rolled nearby will curve inward, not because it is being pulled by an invisible force, but because it is following the geometry of the surface beneath it. On cosmic scales, there is no rubber sheet and no outside space. The geometry itself is space-time, and the entire universe participates in shaping it. When Einstein first wrote down his equations, something unexpected appeared. The equations did not naturally allow a universe that simply sits still. A universe filled with matter would either expand or contract. This result was unsettling. At the time, most scientists, including Einstein himself, believed the universe was eternal and unchanging. To preserve that belief, Einstein added a mathematical term to his equations, a kind of cosmic counterbalance, to hold the universe static. Later, he would call this his greatest mistake. Because when astronomers like Edwin Hubble looked deeper into the sky, they saw the unmistakable signature of expansion. Distant galaxies were receding from us, and the farther away they were, the faster they appeared to move. This wasn't random motion. It followed a precise rule. Velocity was proportional to distance. The universe was not static. It was stretching. This discovery transformed cosmology from philosophy into measurement. The expansion rate could be calculated, the past could be reconstructed, and a startling implication followed naturally. If space is expanding today, then in the past it must have been smaller, earlier, denser, hotter. This wasn't speculation. It was geometry running backward. As the universe contracts in our equations, temperatures rise. Matter behaves differently. Atoms cannot exist. Even nuclei break apart. Eventually, we reach a state where the universe is filled with a dense, opaque plasma of particles and radiation, locked together in constant interaction. Light itself cannot travel freely. This is not yet the beginning, but it is a boundary, the earliest era we can directly test. And remarkably, the universe left behind a record of this time. Not in galaxies, not in stars, but in light. A faint, ancient glow that fills the entire cosmos, carrying with it a snapshot of the universe when it was young, hot, and almost perfectly uniform. Finding that light would change everything, and when it was found, it did more than confirm a theory. It forced us to confront questions that physics still struggles to answer. The light predicted by theory was not supposed to be bright. It would be weak, cold, almost invisible. A whisper from a time when the universe was young enough that atoms could not yet exist. For years, it remained only a prediction, a mathematical consequence of an expanding, cooling universe. If the early cosmos was once hot and dense, then as space expanded, that heat would stretch and fade, filling the universe with a uniform background glow. In 1965, that glow was found by accident. Two radio astronomers, Arno Penzias and Robert Wilson, were testing a sensitive microwave antenna. No matter where they pointed it, a persistent hiss remained. They cleaned the equipment. They removed every known source of interference. The noise refused to disappear. It was coming from everywhere. At the same time, a group of physicists nearby realized what the signal had to be. This was not noise. It was the cooled remnant of the universe's early fireball, light released when the cosmos first became transparent, when charged particles finally combined into neutral atoms and photons were free to travel. The cosmic microwave background. This discovery ended a long-standing debate. Alternative ideas, like the steady-state universe, eternal, unchanging, continuously creating matter, could not explain this omnipresent glow. The hot Big Bang model could. For the first time, humanity was seeing the universe as it once was. A baby picture of the cosmos, frozen in light. But the image was not perfectly smooth. As measurements improved, tiny temperature variations emerged, differences of only a few millionths of a degree. These imperfections were crucial. They represented slight overdensities in the early universe, regions where gravity would slowly amplify structure over billions of years. Every galaxy, every star, every planet traces its origin back to those microscopic irregularities. Yet the cosmic microwave background raised a deeper mystery. Why was the universe so uniform in the first place? Regions on opposite sides of the sky appear nearly identical, even though there hasn't been enough time since the Big Bang for them to exchange information. They should not know about each other. And yet, they agree. Even more puzzling is the problem of order. According to the second law of thermodynamics, entropy, disorder, always increases. Systems naturally evolve from order to chaos, and yet the early universe was extraordinarily smooth, organized, and low in entropy. This is the opposite of what we would expect. The universe did not begin in a messy, chaotic state. It began in a remarkably special one. Why? Pushing our equations further back only deepens the problem. Density and temperature rise without limit. Space-time curvature diverges. The mathematics breaks. This singularity is not a physical explanation. It is a warning sign. It tells us that the theory we are using, general relativity, has reached the edge of its validity. To go further, we need something new, a framework where space-time itself is subject to quantum uncertainty, where geometry fluctuates, where the very notion of a classical beginning may dissolve. And in that uncertain territory, a radical idea emerges, one that may explain both the universe's uniformity and the seeds of all cosmic structure. At the smallest scales imaginable, the universe does not behave smoothly. Quantum mechanics tells us that uncertainty is not a flaw in our measurements. It is built into reality itself. Energy fluctuates, fields jitter. Even empty space is never truly empty. If space-time is subject to these rules, then the earliest universe would have been nothing like the calm, continuous geometry we experience today. It would have been violent, unstable, filled with microscopic fluctuations. And yet, the universe we observe is astonishingly uniform. To reconcile these facts, physicists proposed an extraordinary idea: cosmic inflation. According to this hypothesis, a tiny fraction of a second after the universe entered its hot, dense phase, space underwent a brief but dramatic episode of exponential expansion, not driven by matter or radiation, but by a form of energy inherent to space itself. During inflation, the universe did not simply grow, it exploded in scale. Regions once smaller than an atom were stretched to astronomical sizes. In that violent expansion, irregularities were ironed out, explaining why distant parts of the universe look nearly identical today. But inflation did something even more remarkable. The same quantum fluctuations that jittered at microscopic scales were stretched along with space. Tiny variations in energy density were frozen into the fabric of the universe, becoming the seeds from which galaxies would eventually form. What appears today as a vast cosmic web began as quantum noise. This idea solved multiple puzzles at once. It explained the universe's uniformity. It accounted for the precise pattern of fluctuations seen in the cosmic microwave background. And it provided a natural origin for large-scale structure. Yet inflation is not a complete theory. We do not know what field drove it. We do not know how it started. And we do not know whether it happened only once or is still happening elsewhere. Some versions of inflation suggest that it never fully ends. Instead, different regions of space stop inflating at different times, forming isolated bubble universes. Each bubble becomes its own cosmos, with its own history and physical properties. In this picture, our universe is not unique. It is one region in a much larger multiverse, a vast landscape of expanding space-time where different laws of physics may apply. This is where cosmology becomes unsettling. Because if inflation is correct, then many features of our universe may not be fundamental. They may be environmental, the result of where we happen to exist in a much larger structure. Constants we once thought inevitable may be contingent. And the question of origins shifts again. If inflation set the stage for the hot Big Bang, then what set inflation in motion? And what came before that? To approach those questions, we are forced to confront the deepest unknown in physics, the nature of space-time itself. When physicists try to push beyond inflation, language begins to fail, not because the ideas are vague, but because the concepts no longer fit into everyday intuition. At scales this extreme, even time may not behave the way we assume. In our normal experience, time flows forward. Causes come before effects. There is always a before and an after. But this structure depends on space-time being smooth and classical. Near the earliest moments of the universe, that assumption may break down. At the Planck scale, space-time is expected to become quantum, not a continuous fabric, but a seething foam of fluctuating geometry, where distances and durations lose their definite meaning. In such a regime, asking what happened before the Big Bang may be like asking what lies north of the North Pole. This idea is captured in the no-boundary proposal, developed by James Hartle and Stephen Hawking. In this view, the universe does not begin with a sharp edge in time. Instead, time gradually transforms into space as we move toward the earliest moments, smoothing out what would otherwise be a singularity. There is no initial instant, no first tick of a cosmic clock. Just as the surface of the Earth has no edge, the universe may have no true beginning, only a transition from one type of geometry to another. Other ideas are equally radical. Some models suggest that our universe emerged from a quantum fluctuation, a spontaneous event allowed by the uncertainty inherent in nature. Others propose a cyclic cosmos, where expansion is preceded by contraction, and the Big Bang is actually a big bounce, the rebound of a previous universe collapsing under its own gravity. In these scenarios, the universe is not born once, but endlessly renews itself. What all these ideas share is a rejection of the classical picture of a singular beginning. They suggest that the Big Bang was not the creation of space and time, but a phase change, a reorganization of reality itself. And yet, despite their elegance, these theories remain speculative. We do not yet have a complete theory of quantum gravity. We cannot directly probe these earliest regimes. Our best descriptions rely on extrapolation, inference, and mathematical consistency. This is not a weakness of science. It is its frontier. Because even without knowing the ultimate origin, we have uncovered something extraordinary. The universe has a history. It evolves. It remembers its past in subtle imprints that still surround us today. And those imprints may yet carry deeper clues, not in light, but in vibrations of space-time itself. Signals so faint, so ancient, that detecting them would allow us to listen directly to the universe's first moments. The remarkable thing is not how much we still don't know. It's how much we've already learned. From faint shifts in the color of distant galaxies, we uncovered the expansion of space itself. From a uniform microwave glow, we reconstructed the universe's early hot phase. From tiny fluctuations, we traced the origin of every structure that would ever form. The cosmic microwave background is our most ancient artifact, a snapshot of the universe when it was less than 400,000 years old, long before stars ignited, long before galaxies took shape. It is evidence that the universe had a past, and that its present complexity emerged from simple beginnings governed by precise laws. Yet those laws also tell us where understanding ends. General relativity describes space-time with extraordinary accuracy, but it predicts its own failure at the Big Bang. Quantum mechanics governs the smallest scales, but resists unification with gravity. Between them lies a domain where our most successful theories fall silent. This silence is not emptiness, it is possibility. Future observations may allow us to peer even deeper. Gravitational waves from the universe's earliest moments could carry information unaltered by matter or radiation. Subtle patterns in the large-scale distribution of galaxies may reveal traces of inflation. New theoretical insights may finally unify geometry and quantum uncertainty into a single coherent framework. Or they may force us to abandon assumptions we have not yet recognized. The origin of the universe may never resolve into a single simple answer. It may turn out that before the Big Bang is not a meaningful question, or that our universe is one episode in a much larger cosmic story. But this uncertainty does not diminish what we have found. Understanding the universe is not about reaching a final explanation and stopping. It is about recognizing that every answer opens deeper questions. Questions that reshape how we see reality and our place within it. We are not passive observers of a static cosmos. We are participants in an evolving universe, capable of reconstructing its history from whispers of light and geometry. And perhaps that is the most profound discovery of all, that the universe is not just something we live in, but something we can, slowly and imperfectly, come to understand.